Welcome to this lecture on turbocharging AI inference with NPUs. In the next slides, we'll walk through practical model optimization techniques and hardware-aware design choices that unlock major efficiency gains. Think of this as a roadmap. From quantization and pruning to compiler tricks and microcontroller strategies, we'll connect each technique to real performance and power benefits. This slide shows how NPU architecture and algorithmic optimizations are co-designed for efficiency. On the left, you see hardware features like systolic arrays, INT8 pipelines, and weight stationary flows. And on the right, the matching model techniques such as pruning, quantization, and operator fusion. Together, they reduce data movement, raise MAC density, and deliver orders of magnitude gains in max per millimeter squared. Quantization trades precision for latency, memory, and power improvements. Moving from 32-bit float to 8-bit integer can shrink model size about fourfold, double throughput, and roughly halve energy per inference. To keep accuracy, calibration, quantization-aware training, and percentile scaling are used, while aligning model data types with NPU constraints avoids costly runtime dequantization overhead during execution. Channel pruning pares away unneeded filters to produce much smaller graphs, typically 4 to 10 times smaller, and retraining helps recover any lost accuracy. Toolkits like Vela and Tau then adapt models for accelerators by adjusting memory footprints and exposing wider parallel lanes, effectively turning sparsity into tangible runtime and memory savings on Ethos U-style NPUs. Layer fusion eliminates intermediate DRAM traffic by merging sequences like conv, batch, norm, and relu into a single fused kernel that maps directly onto the NPU. The diagram contrasts the traditional flow that reads and writes intermediates with the optimized flow that issues a single instruction, cutting latency by 30–50% and saving power and SRAM through reduced data movement. Architectural choices such as depth-wise separable convolutions, inverted residual blocks, and sparse attention dramatically reduce multiply-accumulate counts, often by an order of magnitude, without big accuracy loss. At the same time, aligning model blocks to NPU tile geometry examples include MobileNet v3, EfficientNet Lite, and Tiny YOLO ensures high tile utilization without needing hardware redesign. For microcontroller class devices, we rely on tiny working sets and streaming techniques. Sliding, window inference processes, overlapping chunks to fit memory constraints, ping-pong buffers overlap compute, with DMA transfers to hide data movement, and layer-wise checkpointing trades extra computation for major memory savings. These strategies sustain real-time results like 30 frames per second speech or 15 frames per second QVGA vision on low-power hardware. Dynamic classifiers reduce latency by letting confident inputs exit early. A confidence threshold enables skipping 20–40% of layers for many samples, yielding faster results with minimal computation. System-level tactics such as batch size 1, scheduling and interrupt-driven wake-up further improve responsiveness, and overall tests show roughly a 30% average latency drop while preserving peak accuracy for safety-critical tasks. Two key optimizations for large model training and inference are mixed precision and communication overlap. Mixed precision, using FP16 forward passes with FP32 master weights, speeds training by about 1.4–1.8x, while keeping convergence, and fused attention with overlapped communication can cut step time dramatically. The example shows step time reduced from 48 seconds down to 26 seconds by overlapping kernels. Auto-hybrid parallelism balances compute and communication for billion-parameter workloads by combining deep pipeline parallelism with tensor splits and multi-shard gradient overlap. Splitting tensors and dispatching shards in parallel raises micro-batch size and balances compute, delivering measured speedups around 1.41x and substantially lowering overall GPU hour costs for very large training jobs. A practical optimization toolchain starts from quantized, pruned graphs and feeds tools like Vela, TAO, ONX runtime and TVM to perform layout, tiling, and emit NPU binaries. Continuous profiling using EON or ML advisors tracks latency, SRAM, flash, and power, helping teams pinpoint remaining bottlenecks and iterate towards silicon sign-off with predictable performance and resource usage. The end-to-end NPU optimization workflow is iterative. Pick lightweight backbones, quantize to INT8 and prune filters, fuse operators and stream tensors, enable early exits, then benchmark on real silicon and iterate. Repeated outcomes on low-power NPUs include roughly 4 times throughput, 3 times smaller memory footprints, and production-grade accuracy maintained through careful co-design and toolchain optimizations.